Okay, ji, Bismillahirrahmanirrahim. Welcome to another lecture of Modern Control Systems. I'm your presenter Mohammad Rafi Suktai. This is lecture number 5. So, last time we learned about block diagram reduction technique. Rather, we started different techniques how to you can reduce the block diagram at different you can say at different points or at different scenarios. We studied 5 basic techniques. In this lecture, 6 rather basic techniques. In this lecture, we will study an example of block diagram reduction. We will start our next article about signal flow diagram, and then we will see how to find a transfer function with the help of signal flow graph. One would be block diagram reduction, second would be signal flow graph, and another would be how to find transfer function via signal flow graph. So these 3 articles would be our point of discussions for this lecture. First of all, let me summarize what we studied about this block diagram reduction technique in our previous lecture. Let me go to the book. The article which we were discussing was this. I received a question about I received a question in email about these 2 and 3 points, so I will discuss these as well. So this was very simple. Last time we discussed these 6 scenarios. Whenever you have 2 blocks G1 and G2 in series, you can combine them into a single block by multiplying their transfer functions G1 G2. So these 2 blocks in series can be combined into a single block. Similarly, we discussed this in detail in last lecture. Similarly, if you have a summing point ahead of a block and you want to move a summing point behind a block, then what would you need to do? It's simple because at this point in the summing point, you have x1 signal, whereas at this point you have x2. So if you want to move this summing point at this point, then the output shouldn't be changed. X3 should be whatever it is. So we discussed this in this point number 2, that there was a summing point and this is the G and this is x3. In this diagram, your x3 is equal to G multiplied by something over here. What was something over here? It was basically x2 plus x1. So G multiplied by x1, or rather x2 plus x1. So x3 is equal to gx1 plus gx2. So when we want to move this summing point at this point, what would we need to do? With we want end result not to be disturbed. We want x3 there. So if you evaluate this signal over here is something this plus something over here this. These two are added up. What is this? What is this signal? This signal is x2 multiplied by g. And what is this signal? This is x1 multiplied by g. So here we get x1 multiplied by g and plus x2 multiplied by g. So these two signals are same, hence these two systems are same. In both systems, x3 is x1g plus x2g. However, the summing block in the above picture, in this picture is ahead of G, whereas the summing point in this picture is behind G. So in this way we can move our summing point. Next was moving a pickoff point ahead of a block. Okay, one thing which I think was confusing to you people, that I received a question related to that, was this. There was a question. I told you that if you want to extract x2 from this point, if you want to extract x2 from this point, and now you want that this x2 should not be here, rather this pick off point should be here. If you want to move this pick-off point to this location, you simply multiply this with G. Now there was a question. I told you that when you move this pick-off point from here, you can combine this G with any block over here. There was a question that what if we want to combine with G with any block over here? Go ahead, no problem. If there is a block over here, then obviously you wouldn't want this pick-off point to move to this point, because it would hinder the joining of these two blocks. So you have any motive, you might have any intention to move this pick-off point from this location, because I gave you an example that there might be any block on this side, and you want to join this block with this block. So if you want to join this G with something at here over here, then obviously you cannot join unless this pick-off point is removed from here. So you want this pick-off point to be removed, hence you pick this signal from here. So as you wanted to pick x2, however here you have x1, so you need to multiply this signal with G to make it x2. It's just like if in a circuit you want to pick some voltage from at certain point in your electrical signal, then you make a connection over there and you pick that voltage from that point. If you want to pick, for example, if there is a electrical circuit and you want to pick some voltage V from this point, and now you want to move this pick-off point to another point which has some different voltage, and obviously you would be needing to add some additional voltage to compensate for that difference. Similarly, here you have added this G because the uh, the signal over here is not x2, the signal over here is x1. So to make it x2, you have to multiply it with G, because the signal you want to pick off is x2, not x1. Let me remove. I just wanted to address the question that I received over the email. So intention to move this pickoff point from this point to over here can vary. It depends what is the shape of the overall bigger, what is the bigger picture. As an example, I told you that if there is a block over here and you want to combine this G with that block, then you obviously wanted this pickoff point to be removed from here. So that is why we have a technique that you can remove this pickoff point from this point to this point if you multiply this with G, because in the end, what signal you want to pick off is x2. Okay, let's move forward. Similarly, let me erase it from this book. Okay. Similarly, there is another technique, point number 4, moving a pickoff point behind a block. there is a pickoff point ahead of a block and you want to move this pickoff point from here over here to over here, there can be any reason for it. Not essentially that there is a block over here and you want to join this block with this G. In any case, if you want to join this block with this G, then this X1 is hindering your path. Then obviously you want this X1 to be removed from here and you want this pickoff point to be here instead of this location. So you want this pickoff point to be moved behind a block over here. So obviously the signal that you wanted to pick off was X1, not X2. So therefore you will multiply this with 1 over G to make it X1. Okay. Next was moving a summing point ahead of a block. This is similar to point 2. And another sixth one was, I told you that it is very important point, eliminating a feedback loop. If there is a feedback loop in your system and you want to convert this whole feedback loop into a one single block, then we evaluated this expression earlier in our lecture. Let's go there. So yes, eliminating a feedback loop. You had a feedback loop over here and you wanted this feedback loop to be converted into single block. I told you that whatever complex block diagram you have, for example in a plant you have multiple blocks, you have multiple systems, multiple blocks, some signal is going there, another signal is coming from somewhere. But there is a complex batch process in which every system is performing individually and in the end all systems combine to give you an overall output. What you want to, if you want to find the transfer function of this overall system, then obviously you would desire that all these blocks should be converted into a single block. Here is an input, here is an output, and here is the whatever written over here would be transfer function. This is desired. So all the block diagram reduction techniques help you achieve this. Okay, so I think it would be better if we discuss an example of block diagram reduction technique. Example would be from your book. I will discuss this example now in this lecture. So it is example 2.7 page 83. You can refer to it anytime. Okay, let me draw it. You have R of S as an input signal and you have a summing block over here. This is plus, this is minus. I have a book with me. This is a plus, this is minus. Here we have a G1 block. Here we have another summing point. This signal is adding up. And we have another block G2. Then we have another summing block. Then there is another block G3 and then G4, and finally we have output Y of S. Now this Y of S is fed back to the point over here with transfer block H1. This is also fed back to this point having transfer block H3. This is a negative feedback. This is a negative feedback. and this is a positive feedback. If you remember, we discussed negative and positive feedback separately. This was the transfer function for positive feedback, a minus over here, and this was the transfer function for a negative feedback with plus over here. So this is the block diagram. I missed one loop. There is another pickoff point from here and H2, and it moves all the way down here. It is a negative feedback. So this block diagram has been replicated over here. So let's try to reduce this block diagram. Our eventual goal is you have R of S over here, then you have some block, and then you have Y of S. You want to go from here to here using the techniques that you have already learned in the previous table that we have just discussed. So I want you people to pause this video for a moment and figure it out that is there any possibility of combining any two blocks in this complete block diagram? Any two blocks. Can we combine this G1 and G2 using our block diagram reduction techniques? At the moment, we cannot join G1 and G2 due to this summing point between them. Can we join G3 and G2? No, we cannot. Can we join G3 and G4? No, we cannot because there is a pickoff point over here. Can we move this? Can we convert this feedback loop into a single block? No, we cannot because there is a pickoff point over here. So the idea is that what if I move this pickoff point from here to either here to the left of G3 or to the right of G4? What would be beneficial? Obviously, if I move this pickoff point to this point, then it would not be that much, it would not add much it would not complicate my block diagram further, rather it would try to make it simplified. However, if I move this pickoff point over here there is a summing junction, so it can make your block diagram more complicated. So what if I move this pickoff point from here to here? Okay, let's try this. Let me remove this connection. Let me use another pen for it. However, the signal that we were picking was something, if I say that signal over here is A, the signal over here would be A into G4. Signal at this point would be A into G4. So this is not the same signal that we are picking up. Earlier we were picking up some signal A to H2. Now we are picking up a signal A into G4. So we have to make some compensation. It means we need to divide this H2 with G4. We need to divide this H2 with G4 so that this effect of G4 can be nullified. So our block diagram would now be, this would be H2 by G4, H2 by G4, and Let me join it over here. And these two blocks will be combined. It will become a single block, which would be a G3 G4. This single block would have transfer function G3 G4. Now if you visualize this complete loop as a feedback path, so we can convert this complete loop using our technique in this. Is this a positive or negative feedback? This is a positive feedback loop. So we know that for our positive feedback loop, the complete loop can be converted into G over 1 minus GH. So this complete loop would be converted into G3 G4 over 1 minus G3 G4 into H1. So this complete would become a single block. Let me try to redraw it on the next page. So our new block diagram would become R of S plus minus G1, then there is a we have G2 over here. No, we have a summing block over here. We have G2 over here. This is plus, and then we have this feedback loop that we have just reduced would be G3 G4 divided by 1 minus G3 G4 into H1, and that is Y of S. And from here we have a signal with feedback loop gain H2 over G4, which is going over here with a negative feedback. So you can see we have slightly reduced our block diagram from this picture to this picture. What change that we have made? We have combined first of all we moved the pickoff point that was over here to point over here. So after moving the pickoff point, we can join this G3 and G4. So we have joined this G3. After joining this G3 and G4, we have this complete feedback loop. So we converted this complete feedback loop into a single block by using this equation, and this complete feedback loop became G3 G4 over 1 minus G3 G4 into H1, and this H2 is converted into H2 over G4 because to nullify the effect of this G4 while picking off the signal from here rather instead from here. So can we reduce it further? Yes, we can. I can multiply this G2 with this because these are in series. Can I do that? Yes, I can do that. How can I do that? I can multiply this G2 I can multiply this G2 over here, G3 G4 multiply by G2. So block diagram is further reduced. Now can I reduce it further? Yes, I can. How? Can you visualize that this complete is a feedback path? This complete is a feedback loop with H feedback path gain H2 over G4 and process gain G3 G4 G2 over something this. So if I call this block as X, then this feedback path whole can be converted into X over, this is a negative feedback, so I have plus over here, x over 1 plus x into h2 over g4. So I can convert this complete feedback loop into a single block of gain this, that is R of s plus minus g1 and then a single block of x over 1 plus x h2 over g4 and then y of s. Can I reduce it further? Yes, I can. I think I have skipped this loop, this path. Okay, let me draw it again. Here we have h3. Okay, can I reduce it further? Yes, I can. I have g1 and this block in series. So I can join this. I can join this g1 with this block and can write it inside of the block. So this will become x into g1. So you can see that can I reduce it further? Yes, I can. Again, it has become a feedback loop. So if calling it as y, I can reduce this block diagram into R of s y over, is this a positive feedback or negative feedback? This is a negative feedback. So y over 1 plus y h3 and y of s. Putting the value of y and then further inserting the value of this x, you will have this transfer function as, I can rewrite this block as g1, g2, g3, g4 divide by 1 minus g3, g4, h1 plus g2, g3, h2 plus g1, g2, g3, g4, h3, y of s. Input is r of s. So you see, initially we had this bigger block diagram and our end goal was to find a block diagram with something shaped like this. And we established that if we are able to convert this block diagram into this form, then anything that is written over here would be the transfer function of our system. So uh, we applied, first of all we moved the pick of, what was the first step, we moved the pick of point from here to here. Then we had liberty to join this g3 and g4. After joining this g3 and g4, we visualized that there was a feedback loop. We converted that feedback loop into a single block, and then again, after converting this feedback loop into a single block, we again visualize that there is another feedback path that we can reduce. So we reduced that feedback path as well and also combined a block over here by writing it inside of this block. So by combining and then removing feedback path, then again combining, then again removing the feedback loop, then again combining and again removing the feedback loop, we finally concluded um, our transfer function to be like this, and we have reduced our initial block diagram to a point where we can calculate transfer function from that. We have reduced only by using existing block diagram reduction techniques that we discussed over here. Initially, I think we have only used 2 points in this example. First, we used point number two, no, we used point number 4. We moved pick of point divide by g, and then we used point number 6. By using only these 2 points, we have reduced our complete block diagram of multiple blocks into a single block. So hope you have understood this example. We can see that in your book as well. This was the block diagram. This was the block diagram. First of all, he removed the pickoff point and then he joined G3 and G4. After joining G3 and G4, there was a feedback loop which has been converted into a single block, and then this block is then joined with this G2. After joining this block with G2, we have another feedback path, and then that feedback path joining, and eventually we get a block diagram with a single block at hand. So that was all for the block diagram reduction. The next topic that we are going to discuss is signal flow graph models. Signal flow graph models. Just like a block diagram, signal flow graph models are another way to represent any process, any signal, any uh, you can say batch process in an industry or in any system. You can represent any system in terms of a block diagram or in terms of a signal flow graph model. For example, if I write a sample signal flow graph model would be x of s as an I am taking x of s as an input. This is some node variable x1. This is some node variable x2, and this is y of s, which is the output, and this is the loop. We also indicate the direction of the flow. So this is the loop variable 1 over r. This is 1 over s. This can also be 1 over s. This can be anything, x1, x2. So it is actually easy to simplify. As I told you earlier in my lectures, all these techniques actually enable us to look inside into the system properties. There are few things that block diagram enables you to learn about the system, while there are another things that signal flow graph enables you to look into the system. There are few calculations that would be made easy if you are dealing with your system in a signal flow graph model, and there would be few calculation that would be easy if you are dealing with your system in Laplace or in a block diagram model or in state space variables. All these representation techniques have their own usage. All these representation techniques have their own benefit in terms of either calculation simplicity or in terms of the insights that one technique can offer over another technique. So what you need to know is the basic concept that what are these techniques, how to model your system in any of these techniques, and how to importantly how to move from one model to another. For example, if you have a transfer function and you want to move to a state space, you would be able you should equip yourself to be able to move from a transfer function to a state variable model. Similarly, if you have a um block diagram model, you should be able to convert that into a signal flow graph. If you have a system represented in a signal flow graph, then obviously you would be able to convert it into a block diagram model as well. There is a formula by which you can directly calculate the transfer function using signal flow graphs. However, in block diagram reduction technique, no formula exists. In block diagram, you find a transfer function only by reducing the block diagrams. However, in signal flow graph, there is a rule, there is a Mason's rule, which basically enables you to find a proper transfer function using um, an established formula. So you can either find the transfer function of a system using block diagram reduction technique in a block diagram model, or you can find the transfer function of a same system in signal flow graph model using Mason's rule. So whichever suits you, whichever has computational benefit, which either of them has computational simplicity, which computer accepts, depends on the scenario which model to be used. So I have drawn a basic signal flow graph model. These round circles that I have drawn are called nodes, and the variable written next to it is a node variable. A line that I have drawn which joins these two circles or these two nodes is called a branch, and this branch indicates the dependency of input and output. If you say this is, it's just like if I want to draw this one branch as a block diagram, then I would draw it like this: x2 1 over s y of s. So whatever that I we previously write in a block diagram model, we write it as a branch variable, or we can say it the branch relates the dependency of input and output variable. Now, what is this node variable? We have called it a node variable. This node variable, how to write the equation of this node variable? We simply can make use of Kirchhoff Current Law to write the equation of this node variable. It is very simple. For example, if you want to write the equation for x1, then this x1 is equal to x of s plus x2 over r. Simple. X of s plus x2 over r. Simple. Similarly, if you want to write the equation for x2 node variable would be x1 over s. This is x1 over s, and nothing else is coming over here. So it is x2 is simply x1 over s. And if you want to write y, equation for y of s, then y of s is equal to x2 over s. Simple. So you can write equations for node variables using either by KCL or whatever signal is entering into this node. There are two signals entering into this node. One is x1 and another is x2 over r. Similarly, there is only one signal entering into this x2 node, that is x1, and multiply by 1 over s. So x2 is equal to x1 over s. Similarly, for y of s, it is x2 over s. The relationship between each variable is written next to an arrow. So if we say that how this x2 and x1 are related, we can say that they are related by x2 is equal to x1 into 1 over s. So this x2 and x1 are related by this factor, and this factor is the relationship between x2 and x1, and it is written next to the arrow. Now next thing is path. What is path? Path is actually a branch or continuous sequence of branches between two nodes. We can ask that if there is any path between x of s and y of s, you would say yes, there is a path. You can move from x of s to x1, then you can move from x1 to x2, then you can move from x2 to y of s. So there is a series, there is a path with three branches, containing of three branches, by traveling on which you can move from x of s to y of s. So yes, a path exists between x of s and y of s. Next thing is a loop. Is there any loop in the system? Yes, there is a loop in a system. How? Loop is actually a closed path that originates and ends at the same node. For example, if I say we are at x1 and we move from here to following this arrow, we move from x1 to x2. Then following this arrow, we have reached x1 again. That is, we have started our journey from x1 and we have reached back to x1. That this means this signal flow graph has a loop in it. And how many loops are there in this signal flow graph? There is only one loop in this signal flow graph. You can have signal flow graphs with multiple loops as well. So, for example, if there is another loop, let me try to draw another loop. Let me erase this y of s and add another node. Let me add x3 and another node x4 and then another and then y of s. Let's say this is 1 over c. So you see now there are two loops. One is this, you have started from x1 and you have reached x1. Then there is another loop, you have started from x3 and you have reached back to x3. Now there are a number of loops in this uh, signal flow graphs are two. Now are these loops touching or non-touching? This is important thing because it will help you in Mason's rule. Touching or non-touching loops. These are non-touching loops because they do not share any node. However, if there was another loop like this with 1 over L as a gain, then there are total three loops in the system, three loops in this signal flow graph. One is one is this, another loop is this, and then another loop which I have just drawn is this. Now there are three loops in the system. Let me call this loop L1, this loop as L2, this loop as L3. So are L1 and L3 are non-touching? No. L1 and L3 are touching loops because they share this common node x2. You can move from x1 to x2 and back to x1 in loop L1, and you can move from x2 to x3 and back to x2 in loop L3. So this loop L1 and L3 are touching loops. However, L1 and L2 are non-touching loops, and L3 and L2 are also touching loops because they are sharing this node x3. L3 and L2 are also touching loops because they are sharing this node L3. However, L1 and L2 are non-touching loop because they are not sharing any node. L1 is between x1 and x2 and L2 is between x3 and x4. They are totally independent of each other. So these are non-touching loops. So if I say how many non-touching loop pairs are in this system, you will say there is a one non-touching loop pair. There is only one non-touching loop pair in this system, which is L1 and L2, which is L1 and L2. So this was the basic concept about signal flow graph models. We discussed nodes, we discussed what is a node, we discussed what is a branch, we discussed what is a node variable, we discussed what is the relationship, how to write a relationship between two nodes or between each variables. Then we discussed what is a path, then we discussed a loop, and then finally we discussed non-touching loops or touching loops. Finally, let's conclude it with how to find transfer function using signal flow graph. So to find the transfer function using signal flow graph, there was a person called Mason. We make use of Mason's formula or Mason's rule. Now what does Mason rule say? Mason rule say that transfer function of any signal flow graph is equal to summation over k p I j k del I j k divided by del. You only need to find this Pijk, del Ijk and del. Now obviously at this point you don't know what is Pijk, what is del Ijk, what is how to sum these two and what is del. So let's discuss this one by one. I am trying to utilize this space because on the next page I will be doing an example. So Pijk, what is Pijk? Pijk is the kth path from node I to j. For example, in the previous lecture, in this example, sorry, if this is y of s, I told you how many paths are there from x of s to y of s. There is only one path. There is only one path. So k would always be 1 in this case because there is only one path. However, if there would be multiple paths from node I to node j, here node I is x of s and node j is y of s. So Pijk is the kth path. K may be 1, 2, 3 or how many number of, it depends on the number of paths from one node to another. Kth path from node I to node j. And what is del? Del is the determinant of the graph. Obviously, we will find this determinant shortly. And what is the del ijk? Del ijk is the cofactor of that path Pijk. So to sum it, we would first of all find Pijk, then find its cofactor and divide by del. We will get the transfer function of the system. So let's do an example. Let's solve an example using this Mason's rule. We have a system. Let's draw a signal flow graph. This is R of S, node R of S. Then there is another node. There is another node. Then this is Y of S. There is another node. This is another node. So this node is, there is another node over here. There is another node over here. The gain from this node to this node is G3. I think the names of the node are not written. So let's see what are the names of the node. This is also an example from your book. Yes, this is the example. Okay, he has not written the names of the node variables in this figure, so you can obviously write any name that you like, because it has, this Mason's rule has nothing to do with defining the names of your node variables. G3 is the gain from this node variable to this node variable. G2 is the gain from this node variable to this node variable. Similarly, here we have G6 and here we have G7. This gain is G8. This gain is G5. This is G4. This is G1. Now we have loops in this system as well. First loop is this. It has feedback gain H2. Similarly, there is another loop over here. It has feedback gain H3. Similarly, there is a loop over here which has feedback gain H6. There is another feedback loop over here which has gain H7. Okay. So this is our system. We have an input R of S over here and output Y of S over here. We have 4 loops. Let's call these loops as L1, this loop as L2, this loop as L3, and this loop as L4. Okay, let's for the sake of let's write the names of the gains of these two paths over here, G6, G7. So this is L4. So there are 4 loops, L1, L2, L3 and L4, and these are the gains of all the paths, and H2, H3 are the gains of the feedback paths. Now first of all, again pause this video and let me know how many paths are there from R to Y. How many paths from R of S to Y of S? So pause the video and just figure it out. How many paths are there from R of S to Y of S? So as you have seen that there are only 2 paths from R of S to Y of S. There are only 2 paths. One is you are at R of S, you go to this node, following an arrow, then you go to this node, following an arrow. You cannot go over here because the arrow is pointed over here. This is a one-way road. You cannot go backwards. So there is another path following this arrow and then this path. Let us call this as path P1. Path P1 is G1. Path P1 is composed of G1, G2, G3 and G4. Similarly, there is another path which we can call as P2. What is this? You are at R of S and following this arrow you reach this node. Following again this arrow you reach this, then you reach here, and then finally you are at Y of S. There is not a single other path that you can follow for going from R of S to Y of S. So this path P2 is composed of G5, G6, G7 and G8. Now let's find the determinant of the graph after finding the paths. How many paths are there? There are 2 paths, P1 and P2. Only by following these 2 paths you can reach Y of S from R of S. So determinant of the graph, we have a formula for the determinant of the graph, which is equal to 1 minus sum of individual loop gains plus sum of two non-touching loops, or rather I would like to write sum of gain products to make it more understandable. Gain products of two non-touching loops minus sum of gain products of three non-touching loops plus sum of gain products of four non-touching loops, and this goes on until there are no non-touching loops. So let's plug in the values from this graph to this formula. 1 minus sum of individual loop gains. Now how many loops are there? There are 4 loops: L1, L2, L3 and L4. So if I say L1, let's define L1 is equal to G2 into H2. Loop gain of loop L1 is G2 into H2. This is the loop gain of this complete loop. Similarly, the loop gain for loop L2 is equal to G3 into H3. Similarly, loop gain for loop L3 is G6 into H6. Similarly, loop gain for loop L4 is G7 into H7. So instead of writing this G2 H2, G3 H3, G6 H6, G7 H7, I would write L1 L2 L3 L4. So 1 minus sum of individual loop gains. Individual loop gains are L1 plus sum of L2 plus L3 plus L4. So this term is completed. 1 minus sum of individual loop gains plus sum of gain products of two non-touching loops. So tell me how many non-touching loops are there? L1 and L2 are touching or non-touching? These are touching loops. L3 and L4 are touching or non-touching? These are touching because they share this common node. L1 and L2 share this common node. L3 and L4 share this common node. However, L1 and L3 are touching or non-touching? L1 and L3 are non-touching loops. L1 and L4 are non-touching loops. Similarly, L2 and L3 are non-touching loops. L2 and L4 are non-touching loops. So how many non-touching loop pairs are there? I can write L1 and L3 are non-touching loops. L1 and L4 are non-touching loops. L2 and L3 are non-touching loops. And L2 and L4 are non-touching loops. So sum of gain products, this is the gain product of two non-touching loop. Gain of single loop is L1, gain of single loop is L3, and this is the product of this is the gain product of two loops. So we have added the gain products of two non-touching loops minus. Now tell me if there are three non-touching loops. There is no combination of three loops which are non-touching. There is no combination. So this formula ends over here. This formula ends over here because you cannot find any three loops. All of them are non-touching. L1, L2 are touching. So there is no combination of any three loops in this graph. All of them are non-touching. So there is no combination. So our formula ends over here. If there were, we would have moved to this point. If there were any four non-touching, and this goes on. Now this is the first of all, we found out how many paths. Then we calculated the determinant of the graph. Next step is to find the cofactors of this individual paths. Cofactors of path P1 and cofactor of path P2. First of all, cofactor of path P1. How to find cofactor of path P1? To find the cofactor of path P1, simply put all the loop gains that are coming into this path is equal to 0. For example, how many loops are there in path P1? While moving from R of S to Y of S from path P1, we encounter two loops, L1 and L2. L1 and L2 are the loops that are on the way from R of S to Y of S in the path P1. Put L1 and L2 is equal to 0 in this determinant and you would be able to find the cofactor of path P1. That is del, instead of writing I can write 1, obviously, because I am writing it for path 1 del, and for j I can write r, and for k I can write y, 1 ry. This is del ijk. I was path number, j was the initial starting node, and k was the node which was the destination. I was path number, j was source, k was the destination. So here I is 1, r is source, and y is the destination, is equal to 1 minus, when you will be finding the path gain cofactor for path P1, then this L1 would be 0, this L2 would be 0, this L1 L3 due to L1 this would be 0, this L1 L4 would be 0, L2 L3, so it would be simply 1 minus, it would be 1 minus L3 plus L4. Similarly, del 2ry would be equal to 1 minus L1 plus L2, because for path 2 you have loops L3 and L4. Putting this L3 and L4 is equal to 0 in this determinant expression, you will get this. So if we, at this moment I have evaluated all of these three terms of the Mason rule. I have evaluated the paths, I have evaluated the determinant, and I have evaluated the cofactors of the path. Now if I combine all this information and try to write the transfer function of the system, so the transfer function of the system would be now transfer function. I think space wouldn't be enough. So let me try to write transfer function over here. So transfer function would be equal to, now what is in the denominator? So sorry, what is in the numerator? Summation of Pijk and del ijk. That is, what is P1? P1 is G1, G2, G3 and G4, with its del. What is its del ijk? What is its cofactor? 1 minus L3 minus L4. Similarly, for part 2, plus due to that summation, plus G5, G6, G7, G8 into cofactor of path 2, which is 1 minus L1 minus L2. So here is our numerator. So if you have more than 2 paths, this list will increase. So what would be in the denominator? In denominator you have del. So you already know what del is. Del is 1 minus L1 minus L2 minus L3 minus L4 plus L1 L3 plus L1 L4 plus L2 L3 plus L2 into L4. This one. So the overall transfer function, if you put the values of L3, L4, you can obviously find the transfer function in terms of G and H. So from with the help of Mason rule, we have found the transfer function of this system. You can try to formulate the same system into block diagram and try to find its transfer function by reduction techniques. The result would be same. So initially in this lecture we found the transfer function using block diagram reduction technique in block diagram models, and then we discussed an example of finding a transfer function using Mason's rule for a signal flow graph. So I think you would be pretty okay with signal flow graph models and how to find a transfer function of a system represented in a signal flow graph. Again, in case of any questions, you can write to me on rafe.chughtai@uit.edu.pk. The question which was related to the block diagram reduction which I received yesterday, I hope that I am able to answer that question in this lecture while discussing block diagram reductions. However, if there is still any doubts, you can again write to me on the same email ID. I would try to uh, address that in future lectures. So thank you very much. See you in the next lecture. Allah Hafiz.